Dear students, welcome for the ninth session of this theoretical solid state from physical chemistry of second PU. Previously, we have derived the packing efficiency with respect to three different types of cubic unit cells called as simple cubic, body centered, and then the face centered. Okay. So now we will have the concept of imperfections in the solids, or sometimes it is also called as defects in the solids. So before moving to that, let us have the relation between R and A for various cells, cubic unit cells, where R is the radius of the sphere that we have taken. Means if particles are considered to be the points, means they are found to be the lattice points. It is surrounded by R. We are saying that the particles are considered to be the hard spheres that they will touch with each other, such that the radius of that sphere is found to be the R. And what is A here? It is the edge length along the x-axis or y-axis or with the z-axis, because in case of the simple cube or any cube here, cubic system, A is equal to B is equal to C. That is, length is equal to breadth is equal to height. That is why, what is the relation between this one? For SC, I think SCL, simple cubic lattice. When we are deriving, we are getting 2R is equal to A, I think. As it is only the simple cube, the particles are present only at the corners. During the derivation of or calculation of the packing efficiency, we are getting this result, that is R is equal to 2R is equal to what? A. Two spheres get coincided with, that makes the what? Edge length, if the particles are only at the corners. I can say that R is equal to 0.5 times the A. So that is a useful relation that you have to remember while solving some of the numericals related to this solid state. Okay, radius is equal to half times the A or 0.5 times the A, where A is the what length? Edge length. Suppose if it is BCCL, BCC means body centered cubic lattice. We are getting the body diagonal there. So that body diagonal is given by 4R. When you are deriving that, we are getting this value actually. AD we are actually calling that. AD is equal to R plus R plus R plus R. That is called as body diagonal. But that is equal to cube root of A. Cube root of this one into A. It is cube root first. Cube root of this into what? A. R is equal to root 3 by 4. Root 3 is 1.73 something divided by 4. On simplification, I will directly write the final answer only. 433 times the which one? A. R is equal to what? 0.433 into which one? A. If it is what? CC? BCC lattice. Similarly, the third one is FCC lattice, face centered cubic lattice. Or we can choose that in the form of HCP or CCP also. There we are getting the phase diagonal. That phase diagonal is given by 4R. Phase diagonal is 4R. 4R is equal to, during that simplification, we are getting the value as root 2 into A. Though these three results are obtained when we are calculating the packing efficiency with respect to separately the SC or a BCC or it may be the FCC. Okay. So means 4R is equal to root 2 into A. R is equal to root 2 by 4. Root 2 is actually 1.4 something divided by 4. If I simplify that, it becomes 0.3535 times this one. Okay. So those are the three different results that you have to remember with respect to SC, BCC and FCC. R is equal to 0.5 times the A for SC lattice. R is equal to 0.433 into A with respect to BCC lattice, whereas R is equal to 0.3535 times the A with respect to FCC lattice. Similarly, the internuclear distance, or if it is ionic crystal, inter-ionic distance, it is given by what? 2R. Interatomic, or it may be the intermolecular, or sometimes if it is ionic crystal, it is inter-ionic distance. It is given by what? 2R. For SCL, internuclear distance is 2R. It is directly A. It is directly A. For BCCL, body centered cubic lattice, R is equal to that much means what is 2R? 2R is equal to what? 2R is equal to double times, that is 0.866 times the which one? A. 0.866 times the A. Whereas with respect to FCC lattice, 2R is internuclear distance or interionic distance or intermolecular distance. 0.3535 into double times means it is on simplification 0.707 into A. Okay. So this is how you have to remember the values with respect to that. This is the radius value. Here it is the internuclear distance. It is just the twice that of the which one? Radius. Okay. So these are the final numericals that you have to remember while solving for the competitive as well as the theoretical numerical values or theoretical based which one? Numerical problems. Okay. So now we will move on to the next concept that is called imperfections in solids, or it is also called as the defects in solids. Imperfections in solids, or sometimes it is also called as the defects in solids. Defects in which one? The solids. So we know that the solids means it is the regular arrangement of its particles, maybe in the form of an atom or a molecule, or sometimes it may be the which one? Ions. Then what is that imperfect here? Means there is a slight change in the arrangement. Means what is that? There is a deviation in the arrangement of regular arrangement of the particles in the crystal lattice refer to which one? Imperfections in solids. Means any deviation that occurs due to the irregular arrangement of, or we can say that as if by using the deviation means it is a regular arrangement. Any deviation in the regular arrangement of the particles with respect to the crystal system is called as the imperfections of solids, or it is also called as the defects in solids. So here these defects may be due to either the presence of the impurities, or sometimes due to the displacement of the which one? The particle arrangement. Means the change in the position with respect to the particles in the given crystal lattice refers to which one? Defects. So here there are three types of defects in solids. There are three different types with respect to the solids. One is the point defects. The second one is line defects. And third one is the plane defects. Okay, let's have the rough diagram. Let us first. So I think this is the one dimensional. This is a two dimensional. Okay, this is the what? Three dimensional. That already shown for you. So now they are found to be the perfect solids because the particles are exactly arranged. Now, what makes this one to be the difference or the imperfections? Suppose if one of the particles gets disturbed from its position, it is called as the point defects. Point defect means only a single particle gets changed its position, or there is a irregularity arrangement with respect to one of the lattice point. That is what is called as what defects? The point defects. Then what is the line defects? Not the one lattice point, but whole of the, which one? Any one of that one, I don't know that. these particles are gets missing throughout the whole line. Means it is throughout the whole line, we can say that it is called as what defects? Line defects. Then what is that plane defect here? This is the first plane, this is the second plane, this is the third plane, this is the fourth plane, this is the fifth plane, and so on. We are having a three-dimensional nature. Suppose if one of these particles are plane, whole of the particles gets disturbed, then it is called as which one? The plane defects. Suppose if only one particle gets disturbed along the given one dimension, then it is called as what? Point defect. If whole of the particles aligned in a single line gets removed or it may be detached, then it is called as what defects? Line defects. If whole of the particles in the given plane, because we are having n number of planes with respect to the what dimensional? Three dimensional. One plane particles totally gets deleted or it may be irregular arranged, means it is called as what defects? The plane defects. But as for the syllabus, we didn't have this and this. What is that? We didn't have the line defects and then the plane defects. We are having only the one that is called as the point defects. Okay? So these point defects are of three types. Stoichiometric defects, non-stoichiometric defects, and then the impurity defects. What these are? All these are the examples with respect to which one? The point defects. Means any deviation in the arrangement of only one of the lattice points in the given crystal lattice with respect to one dimension is considered with the what defect here? It is the point defects. Okay. So let us have the discussion one by one. The first is the stoichiometric defects. We are going to concentrate only on which one? The types of point defects. Types of what defects? Here it is the point defects. The first one is what? Stoichiometric defects. Stoichiometric defects. It is the first what defect here? It is a point defect. It's a what defect? Point defect. So the point defect has occurred such that there is no change in the stoichiometry of the crystal system. Stoichiometry means indirectly we are saying that it is a chemical composition. Means what is the ratio of those particles? If that doesn't get disturbed, means it is called as stoichiometric. It is first a what defect? The point defect that has been occurred due to the maintaining of the same chemical composition of the given crystal lattice, which is called as what defects? The stoichiometric defects. So here, these stoichiometric defects are of two types. The first one is two types again. One is, the first one is considered to be the which one? The vacancy defect. The first one is found to be the vacancy defect, and then the second one is considered to be the interstitial defect. Interstitial defect. Which and which? The vacancy and interstitial. Okay, let's have now first, let us have the particle of, for example, x here. This is x here, x here, x, 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 x. Let us say this is another crystal, for example. So let us take the same x, for example, x. I don't know whether it is an atom or a molecule or it may be an ion. What x are? They are the particles with respect to which one? The crystal system. Now it is considered to be the, just I am writing only the two dimension here and not the three dimension here. Okay. Now these two are considered to be the what? The perfect solids. Why? Because there is a regular arrangement of the particles called as which one? X axis. Sorry, what are the x particles. Now it becomes an imperfect here. Why? Because there is no presence of a which one? Particle called as X in this particular position. Similarly, this is not here, but it enters into here. This is called as vacancy defects, and that is called as the interstitial defect. So then what is the vacancy and then the interstitial here? First, vacancy defect is an example for a what defect here? Stoichiometric defect, because there is no change in the chemical composition of that particular crystal system, where the particle has been missed from its lattice point by creating the hole, or it may be the vacancy. That is why it is called as what defect? The vacancy defect. Interstitial defect is also an example for a what defect? Stoichiometric defect, and that is due to the missing of the particle from its original position into the interstitial position. Means the particle X which has to be present here, it has been entered to here. This position is called as interstitial position, means intermediate. It is not the exact position. If that be the case, it is called as what defect? The interstitial defect here. So here, this decreases the density. It increases or nearly maintains the density of the crystal. Why? So here the volume occupied by the crystal is found to be same, but there is a vacancy here, no doubt. Means the volume is constant here, before and after. Okay? Some particles are missing, means its mass is less right now as compared to the perfect solid. Mass becomes less, but the volume of that particular crystal system is found to be the same. Volume is same, mass is less, means the density with respect to vacancy defect goes on decreasing. Where is that? First, according to that, we can say that the density remains the same, because no change in the mass and no change in the volume. That is why first the density remains the same. But suppose if some extra particles has been entered here, I don't know that. What happens? The mass gets increased, but the volume of that particular system remains the constant. Therefore, it is found to be the increase in its mass with keeping the volume constant, means the density goes on increasing. Usually, it gets increased to a maximum extent, and in some cases, the density remains the same with respect to what defect? Interstitial defect. First, both are what defects here? The stoichiometric defects that has been caused due to the missing of some of the particles from their original lattice points refers to which one? Vacancy defects. Vacancy defect usually decreases the which one? Density of the crystal. Whereas that interstitial defect is also an example for a stoichiometric defect that arises due to the what? The entering of the or missing of the some of the particles from its original lattice points and enters into the interstitial or the intermediate position. That is why it is called as interstitial defect. So that interstitial defect may either increases the density of the crystal, or sometimes it remains almost the density of the crystal. Okay. So this extension, if it is with respect to the ionic crystals, with respect to which one? Ionic crystals. Now they are found to be the two different defects called as the vacancy defect can also be mentioned in the form of the Schottky defect, whereas the first one is Schottky defect. And then we are having the B is called as Frenkel defect. So here these two are with respect to strictly the ionic crystals. Schottky defect and Frenkel defect doesn't leads to which one? The general for atomic crystals or the molecular crystals, but it is strictly applicable for the two types based on or with respect to which one? The ionic crystals. Ionic crystals means what? The particles are of oppositely charged ions which are held together by a what bond? Electrovalent bond, or simply it is called as ionic bond. Okay. So now So now all are vacant here right now. X plus 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 and x plus. Let us take this as y minus 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 y minus. Means it is an ionic crystal of xy, where x is a cation called x plus and y is an anion called as y minus. I will write the same thing here. Same x plus x plus x plus x plus plus x plus x plus x plus. Okay. Now we will have the anion in the form of which one? Y minus 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 and then y minus. Now can I say that these two are perfect? Which one? The crystals, perfect solids. Why they are? Because why they are perfect solids? Because we are having the exact arrangement of the cations and then the anions. In both the cases, I think approximately I will mention that as 8 cations and 8 anions. Here also 8 cations and 8 anions. Now, first it is an example for a what? The perfect solid. Okay. Now, how to make this one to be the what? Schottky defect. X plus gets removed here, y minus gets removed here. So this is called as Schottky defect. X plus I will remove here, and this has entered here. What is this? For example, I think I removed this, therefore it is x plus. So this now becomes an imperfect, or it is also called as a defect, and that is particularly the maintaining of the same. Which one? The ratio. Because how many cations and how many anions are there here? Previously it is 8 cations and 8 anions, but here it is 1 cation is missing and 1 anion is missing. Means they are maintaining the ratio of 7:7. Again it is 1:1. But there, that's also same I think. So here 8:8, but this is not in the exact position, but it is in the intermediate position. That is why sometimes it is called as Frankel defect. Then what is Schottky defect and what is Frankel defect here? It is a what defect? Stoichiometric defect in ionic crystals. Because it is not applicable for either the atomic or it may be the molecular. It is strictly applicable with respect to which one? The ionic crystals. Means it is a stoichiometric defect with respect to the ionic crystals due to the missing of equal number of cations and anions. It is totally the missing of both the same number of cations and anions. Suppose here I may have missed how much? 1 cation and 1 anion. Not only 1 and 1. If it is 2, here also it is 2. If it is 3, here also it is 3. If it is n number of cations are missing, n number of anions must be missing. Means we have to maintain a constant ratio. And that defect is called as Schottky defect. Means the stoichiometric defect with respect to ionic crystal due to the missing of equal number of cations and anions from their original lattice points is called as what defect? Schottky defect. Then here it is also a stoichiometric defect with respect to the ionic crystals that has been due to the entering of the cations or any one of the ions, preferably the cations we are selecting. Preferably the cations are entering into the interstitial positions from their original lattice points. Means instead of placing at their original point, what you have to do? They have to be entered into the interstitial positions. That is why it is called as the Frankel defect. This is indirectly called as the vacancy defect, and this is called as which one? The Frankel defect. Can I say that the density goes on decreasing here, the density remains the same. Due to the Frankel defect, what happens? The density remains the same. Why? Because we are having the same number of cations and same number of 8 as 8. 8 and 8 is to 8 means the mass remains the same and the volume remains the same. But here it is Instead of 8 cations and 8 anions, we are having right now 7 cations and 7 anions by occupying the same volume. Therefore, the mass decreases, volume remains the same. Therefore, the density gets decreased. Means it is indirectly the extension of which and which, the extension with respect to which and which, the vacancy defect and then the interstitial defect. Frankel defect, Schottky defect is the extension with respect to vacancy defect, strictly applicable for the ionic crystals. Similarly, Frankel defect is nothing but the vacancy defect which is applicable for the ionic crystals. Okay. Then, what are the differences that we can expect between these two? What are the various differences between these two? Just we will have the differences between those two. Make the differences. So I think same definition. The first difference itself is the definition. Means missing of equal number of cations and anions from their lattice points is called as what defect? The Schottky defect. There, it is the entering of the cations preferably from their original lattice points into the, which one? The interstitial positions, that refers to the what defect? The Frankel defect. So here the density of the crystal decreases. Here the density with respect to this one remains the same. Nearly remaining the what? Same. Okay. Then this is observed in ionic crystals or solids having high coordination number of either 6 or it may be the 8. For example, sodium chloride or cesium chloride. This is having a FCC structure and this is having the BCC. FCC means it is 6 coordination number. Cesium chloride BCC means it is 8. But this is observed in the ionic solids having low coordination number of either sometimes 2 or it may be the 4. For example, zinc blend structure. Or I can say it takes AgI or it may be the AgCl or it may be the AgBr. That exhibits, this is having a coordination number of 2, this is having a coordination number of 4. This is coordination number 8 and this is coordination number 6. So that is the difference with respect to the which one? The Schottky defect and then the Frankel defect. So this is shown by the solids having same size of cations and anions. When we are expecting this is shown by the ionic solids having the same cationic size and same anionic size. Means same size of both the cations and then the anions. But here, this is shown by the solids having a larger anionic size and smaller which size? Cationic size. Means the anionic size must be very much larger compared to that of the cationic size. Means it is having the coordination number of either just only the 2 or maybe sometimes 4, and that refers to the what defect here? It is the Frankel defect. Okay. So and finally the examples that has been given, the examples related to this one is sodium chloride and cesium chloride. There it is found to be the zinc blend and then the silver iodide. But the thing is, AgBr can exhibit not only the Schottky defect but also the one exception with respect to this one is the Schottky defect is, the silver bromide is exhibiting not only the Schottky defect but also the which one? The Frankel defect. So that is one of the major thing that we have to observe in case of the which one? The silver bromide. Okay. So this is a stoichiometric defect. That stoichiometric defect first broadly classified under 2 different categories called as the vacancy defect and then the interstitial defect. So that extension of the vacancy defect is called as Schottky defect. The extension of the interstitial defect is also called as the Frankel defect. But these two, Schottky and then the Frankel defect, strictly applicable for the which one? The ionic crystals. Suppose in case of the defect or the stoichiometric defect that has been observed, where we are having the missing of equal number of cations as well as which one? Anions from their original lattice points refers to what defect? The Schottky defect. Whereas the same stoichiometric defect with respect to the ionic crystals, where the original, one of the ions, preferably the cations, are displacing from their original position and enter into the what positions? Interstitial position, that refers to the which one? The Frankel defect. Schottky defect, the number of particles get totally missing, means its mass decreases, therefore the density of the ionic crystal gets decreased in case of Schottky defect, but the density remains the same in case of the what defect? The Frenkel defect. Then the Schottky defect is observed in case of the ionic crystals where the coordination number is bound to be higher in the range of usually the what and what, either the 6 or it may be sometimes 8. Whereas the Frenkel defect is observed in the case of the ionic solids or the crystals having the coordination number of either sometimes 2 or it may be the 4. Then the Schottky defect is shown by the ionic solids where the sizes of both the cations and then the anions are found to be almost same. Whereas the Frenkel defect is observed in case of the ionic crystals where the anionic size is found to be very much greater as compared to that of which one? The cationic size. Okay. So the more exception for this one is the silver bromide is exhibiting not only the Frenkel defect but also the which one? The Schottky defect. Schottky defect as well as the Frenkel defect. Okay. So that is the first type of point defect called as yaradu. It is called as the stoichiometric. Means we have to maintain the what? Same chemical composition till to the end. That is why it is called as which one? The stoichiometric defect. Okay. Now we will move on to the second one, that is called as non-stoichiometric, and third one that is called as impurity defect. So let us have the first in the form of, second in the form of impurity defect. Okay. So here as if the word itself mentioned means the defect or the disarrangement or irregularity is due to the presence of not the original particles present in that one, but it is due to the other particles with respect to the given crystal system is called as what defect? The impurity defect. So for example, you can have another one here. Okay. Let us take the crystal of sodium chloride here. It is Na plus first. Na plus, Na plus, Na plus, Na plus, Na plus, Na plus, and Na plus. Okay. Now we will have the second one in the form of which one? The Cl minus. Cl minus, Cl minus, Cl minus, Cl minus, Cl minus, Cl minus. Now it is a pure or the perfect the sodium chloride or the rock salt structure here, crystal. Because we are having Na plus and Cl minus only, means it is perfect. Now, during its preparation, during its what? Preparation. In the preparation of sodium chloride, a smaller amount of strontium chloride if present, what happens here? Each Sr2 plus, because it is a bivalent, replaces 2 Na plus ions, creating one hole. Creating what? One hole. That makes first an imperfect. Suppose if we are having a 1 kg of sodium chloride, suppose if we are having 1 point something grams of strontium chloride is present in the form of impurity. Strontium chloride means SrCl2, Cl minus is nothing problem, there is no problem with respect to the Cl minus. But instead of Na plus, there is a presence of which one? Sr2 plus. Suppose if Sr2 plus is present here, what's that here? Sr2 plus. The whole crystal is here, 1 Na plus cannot be replaced by 1 Sr2 plus because Sr2 plus is a divalent and Na plus is a monovalent. Now it is not electrically neutral. So for that what happens here? One of the Na plus has been removed, another Na plus has been removed and create a hole inside this. This is first a perfect or an imperfect here. It is imperfect. It is also a point defect. But the thing is, there is a presence of Na plus and Cl minus along with an unknown impurity in the form of which one? Sr2 plus. Means Sr2 plus in the strontium chloride, SrCl2 is made to be the impurity, and that particular defect is called as what defect here? It is the impurity defect. Means instead of the original substance if present, another minor part of the second substance is present, and that acts as a impurity, and that changes the stoichiometry of that one. That is why it is called as which one? The impurity defect. Okay. Let us have the third one or the last one. The last one that we have to study under this point defect is the non-stoichiometric defect. In that itself it has mentioned. Non-stoichiometric means no maintaining of which one? Original chemical composition. Non-stoichiometric defects. It is also a what defect first? A point defect, which is due to the non-maintaining of its original chemical composition. Means the arrangement is in such a way that it gets disturbed, and that is due to the non-maintaining of the original which one? Chemical composition. That refers to the which one? Non-stoichiometric. So here these are of two types. Non-stoichiometric defects are of how many types? The two types. What is the first one? One is metal excessive and another one is metal excessive defect. The second one is metal deficiency defect. Metal deficiency defect. Non-stoichiometric are of two types, either the metal excessive defect or it may be the metal deficiency defect. So these are again two types. What's that? One is small a, let us mention, metal excessive defect. MED means metal excessive defect due to anionic vacancies. Anionic vacancies. The second one is metal excessive defect due to extra metal cations. Extra which one? Metal cations. Both are metal excessive defect. But the thing is, that is due to the two reasons. One is due to the creating the anionic vacancies. The second one is due to the extra metal cations. So let us have first. Okay. Let's have first Na plus, Na plus, Na plus, Na plus. Na plus. Let's have the second in the form of anion, that is called as Cl minus. Cl minus. Okay. Now it is perfect or imperfect here? It is a perfect ionic crystal of which one? Sodium chloride. Okay. When this sodium chloride of pure, when it is heated in support of a small sodium vapor, in support of a which one? Small sodium vapor, means we are having the Na in the form of a vapor. What's that? When the pure which crystal? Sodium chloride crystal is heated in support of the small sodium vapor, what happens? As if we know that it splits into what and what? Na plus and then the Cl minus. It split into which and which? Cl minus and Na plus. So if this be the case, one Cl minus, for example, one Cl minus has been transferred into this Na plus with the Cl minus present in this, it is removed in the form of volatile sodium chloride. Means it starts to get vaporized. Now this becomes a vacant here right now. But it is not electrically neutral. Why? Because we are having, I think, more cations and less anions. Means the charge is electrically not neutral. For this what happens? The electron, I think I done mistake here. It is Na plus and then which one? Electrons. Na plus and then electrons. To maintain that electrical neutrality, what happens? This electron get entered in this, which one? Anionic position. Which is the anion here? It is Cl minus. So here, when we are heating in support of a small amount of the sodium vapor, what happens? Sodium vaporized gets to form Na plus and Cl minus. That outside Na plus ion takes away the Cl minus present in the crystal lattice and is removed in the form of volatile what chloride? Sodium chloride. But to maintain an electrical neutrality, what happens? This anionic Cl minus has been entered into is entered by the freely moving which one? Electron. And this is called as F center. So first, what is this here? 1, 2, 3, 4, 5, 6, 7, 8. 8 Na plus. How many Cl minus? 1, 2, 3, 4, 5, 6, 7. Means there is a change in the chemical composition. Initially it is 8:8, but here it is 8:7. There it is 1:1. Here it is not in a exact ratio. It becomes a fraction. Means it loses its original chemical composition. That is why first it is called as non-stoichiometric. It's going to be the what? Non-stoichiometric. So here, whether the cations are in excess or anionic excess, cations. Cations means usually the metal. Therefore, it is called metal excessive defect. But how that metal excessive defect due to the creating of vacancy by the anions, which the anion here it is Cl minus. Cl minus gets vacated, therefore it is called as anionic vacancies, and this is called as F centers. This is also called as what centers? F centers. F means Faber. Faber means color. It gives a yellow color to the or golden yellow color with respect to sodium chloride, because the freely moving electrons gets excited to the higher state. Excited electrons what they become? They become highly unstable and then start to emit the radiations falling in the UV region, visible region, which gets a golden yellow color. Means sodium chloride on heating we are getting the golden yellow color because of the creating of the what vacancies? Anionic vacancies. So that is why it is called metal excessive defect, but it is due to the what? Anions are vacating here. So then there is a second one that is called as okay. So here it is Zn2 plus, Zn2 plus, Zn2 plus, Zn2 plus, 2 plus, Zn2 plus, Zn2 plus, and then Zn2 plus, zinc ion, cations. Now we are having the oxide ions O2 minus, 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 and then the O2 minus. Okay. Now it is a pure ionic crystal of zinc oxide. Here cation is Zn2 plus and anion is which one? When this zinc oxide in the form of solid, which is found to be the colorless or white, when it gets heated, what happens? First it is converted as Zn2 plus O2 minus. First the ionic bonds start to break. So this on converted into further Zn2 plus plus. Half of the oxygen has been removed in the form of gas, along with the loss of how many electrons? 2 electrons. 2 electrons. Oxygen being the what? Oxygen being the what? Gaseous, it removed out. And the heating of zinc oxide also removes the which one? The electrons. Means here Zn2 plus means oxide is removed in the form of the oxygen gas, but as if we are heating without the support of an external agent, the electrons are also gets excited. So that this becomes the vacant, and that is due to the how many cations and how many anions prefer before and after? Before it is 8 Zn2 plus and 8 O2 minus, but after heating we are getting only we are having the 8 Zn2 plus but only 7 O2 minus. Means again it is what defect? Metal excessive defect. But here the metal excessive defect is due to the which one? Extra metal cations, because as if there is no oxide ion, because that oxide ion is decomposed as the volatile oxygen gas along with the loss of the which one? Electrons. Therefore we are having the metal excessive defect due to the what? Extra metal cations. Again there is a loss of a which one? Stoichiometry. That is why first it is called as non-stoichiometric. Okay. And lastly we will have the third one in the form of metal deficiency defect. This is observed only in case of the transition metal compounds, because the transition metals or the D block elements will have the variable oxidation states. Okay. So let us have the diagram related to that as first we will take Fe2 plus, Fe what plus? 2 plus, Fe2 plus, Fe2 plus. I will just write as Fe2 plus, Fe2 plus, Fe2 plus, Fe2 plus, Fe2 plus. Ferrous ions here. Now we are having the O2 minus, O2 minus, O2 minus, O2 minus, O2 minus, O2 minus, O2 minus and O2 minus. So here initially we are having 8 Fe2 plus and 8 O2 minus. Perfect or imperfect here? Perfect. Okay. Now we know that iron exhibit the two most variable oxidation states of +2 and then +3. Among that Fe3 plus is found to be relatively more stable as compared to that of Fe2 plus. Why? Because Fe2 plus is converted to Fe3 plus by the loss of one electron such that it gets a set of half-filled configuration. So that all we will discuss in the D block elements. Fe3 plus, why it is more stable? Because it is having a d5 configuration. D5 configuration means it is a set of half-filled d orbitals. Any half-filled orbitals will have the most stability. So here usually without heating, when ferrous oxide gets exposed to air, it slowly converted to which one? Ferric. Okay. So here this is converted as Fe3 plus, Fe1 plus, 3 plus by oxidation. But it is not maintaining the electrical neutrality, because for a given solid, ionic solid, it has to maintain the perfect neutrality. So here 2 of Fe3 plus is replaced by 3 of Fe2 plus. Why? Because we have to maintain an electrical neutrality. Means once Fe2 plus is converted to Fe3 plus, means there is an increase in the positive charge. It is not neutral. Means one Fe2 plus is not equivalent to one Fe3 plus. Then how to make that electrical neutrality here? We have to remove the 3 Fe2 plus. 3 of the which one? Fe2 plus has been replaced with respect to 2 of the Fe3 plus, because plus 3 into 2 is plus 6. Here 3 into plus 2 is also plus 6. Means how much Fe2 plus has to be replaced by how much of Fe3 plus? 3 of the Fe2 plus has to be replaced by 2 of the Fe3. So 3 of the Fe2 plus has been replaced by 2 of the what? Fe3 plus. Means this had to remove, this also had to remove, and here we are having the Fe3 plus. Okay? Fe2 plus, Fe2 plus, Fe3 plus here, Fe2 plus, Fe2 plus, Fe3 plus and this one. Okay? Means here we are having how many cations? 1, 2, 3, 4, 5, 6 and 7. How many anions are there? Oxygen 1, 2, 3, 4, 5, 6, 7, 8. Means how many cations and how many anions are there here? 7 cations and then 8 anions. So here the thing is 7 cations plus 8 anions. Means which is in excess here? Anions are in excess or cations in less or deficiency. Cations means indirectly it is called as metal. Therefore it is called as metal deficiency defect. So here among the 7 cations, 2 Fe3 plus and 5 Fe2 plus. Among this one, what we are having? The 3 of the Fe2 plus has been replaced by 2 of the Fe3 plus. Therefore, totally we are having 2 Fe3 plus. These 2 are Fe3 plus and the rest 5 are found to be the Fe2 plus. That is why there is a deficiency with respect to the which one? Metals or the cations. That is why it is called as a metal deficiency defect. Therefore, the formula for this one is going to be Fe 0.95. This is the formula of the oxide. Because it is why it is not exact FeO or Fe2O3 or FeO3 or whatever it may be. Because as it is losing its chemical composition. That is why it is called as a non-stoichiometric. The formula for that one is between Fe 0.95 with what? What is the meaning of that? For every one oxygen we are having only 0.95 of iron. Among that iron we are having the 2 possibilities. One some may be in the form of Fe2 plus and some may be in the form of Fe3 plus. Means this type of metal deficiency defect is observed only in case of the transition metals having the variable what states? Oxidation states. Sodium chloride doesn't exhibit this. Magnesium chloride, strontium chloride doesn't exhibit this. Why? Because they doesn't have the variable oxidation state. Means any transition metals which is having the variable oxidation states will have the what? The metal deficiency defects. Okay. So this is about the non-stoichiometric defect. Among that we are having the metal excessive defect. The first one is metal excessive due to the anionic vacancy and the second one is metal excessive due to the extra metal cations. So here if the external metal has been heated such that there is a creation of the anions or vacancy in the anions and that makes the electron has been trapped into that one, then those are called as F centers. F centers are also called as favor, means they are called as color producing centers. More the number of excited electrons, more is the number of F centers. More the F centers means more is the intensity of the color. And lastly we are having the metal deficiency defect which is observed in case of the metals having the transition variable oxidation state, preferably the D block elements, or sometimes it may be also called as the transition elements. Okay. So this is about the total imperfections, or it is also called as the deficiencies, imperfections, or it is also called as defects in the solids. Okay. Now we left with another 2 properties. One is electrical property in solids and then the magnetic property in case of solids. In electrical property we are having the band theory of solids, and that band theory of solids decides the solids can be of 3 types called as a conductor, insulator and then the semiconductor. Based on the forbidden energy gap between the valence band and then the conduction band, we are having the conductors, semiconductors and then the insulators. Again the semiconductors are of 2 types called as N-type semiconductors and extrinsic semiconductors and then the intrinsic. Okay. Again the extrinsics are of 2 types, either it may be in the form of the N-type semiconductors and then the P-type semiconductors. So that is about the electrical property that I have to discuss according to the band theory of which one? Solids. Okay. And lastly we are having the magnetic property. So that magnetic property with respect to solids are of 5 types called as diamagnetic substance, paramagnetic substance, ferromagnetic substance, ferrimagnetic substance, and finally the antiferromagnetic substance. So they all depends upon the number of which one, unpaired electrons or it may be the paired electrons. Okay. So these two, that is the electrical property and then the magnetic property, that all we will discuss in the next session of this particular chapter, that is called as solid state. Okay. So thank you.